Greetings to everyone. Myself, Jerlin Ajit Davidson, Assistant Professor from ECU Department of Christian College of Engineering and Technology. Today we are going to discuss and revise the topic cache memory from the Unit 5 of Computer Architecture. So let us see what is cache memory. So in the introduction part, so cache memory is a very high speed memory, right? So which is used to increase the speed of the program execution, right? So normally in the computer system and all, the main memory is composed of dynamic RAM cells, right? So one of the programmers wants the system to be very fast, flexible, and uh, very responsible, right? For that, so the dynamic RAM alone there is means the system will be slow, and if it is composed of fully static RAM, that is SRAM, means the system will be very fast, but the cost of constructing the system is will be very high, and so it is impossible to compose the main memory by using static memory cells alone. So hence, to improve the system performance or to improve the speed of the system, along with the dynamic memory, that is along with the main memory, they have included a small part of static RAM to increase the speed of the program, to increase the speed of the system. That small part of static memory, static RAM or SRAM, is called cache memory, right? So hence we can say the cache memory is used to increase the speed of the program or speed of the system, right? So hence it is called a very high speed memory, right? And next, access time to cache memory is less compared to that of the main memory. So while accessing the main memory, the time will be more, and while accessing the cache memory, that considerably the time required to access the cache memory is less, right? And what will be there in the cache memory? So cache memory is nothing but, so it contains a portion of the main memory, right? So in the main memory, the entire program will be there, and in the cache memory, some portion of the program which is stored in the main memory will be there in the cache memory, right? So for example, we can say the entire program is there is in main memory, and the current part of the program which is being executed will be there loaded into the cache memory. So we can say a small portion of the program is there stored in the cache memory, right? So next, so when CPU, that is the processor, attempts to read a word from the main memory, it will check whether uh, it is in the main memory or it is in the cache memory, right? So if it is in the cache memory, then the word, when the CPU attempts to read the word is read from cache, or it is delivered from the cache. So this diagram shows the the implementation of the cache memory in between the CPU and the main memory, right? So the cache memory holds a part of the program from the main memory. So next is mapping. So mapping means it is nothing but the different techniques which are used to store or copy the data from the main memory to the cache memory, right? So in what way we are copying the data, or uh, uh, storing the data from the main memory into the cache memory. That is called mapping. Mapping means nothing but copying a portion from the main memory to the cache memory, right? So that is called mapping, and in the mapping there are three different techniques. First one is direct mapping, second one is associative mapping, and the third one is set associative mapping, right? The second method, associative mapping, is also called as fully associative mapping. So these three are the mapping techniques in the cache memory. So first let us see in brief about the direct mapping technique. So this direct mapping technique is the simplest way to determine the cache locations in which to store the main memory blocks, right? So I already told the mapping means nothing but the method to copy or store the blocks of memory from main blocks from the main memory into the cache memory, right? So here direct mapping means it is the very simplest way to determine in which location, in which cache location we have to store uh, the memory blocks from the main memory, right? So here the direct mapping technique is implemented using a diagram, right? So here there is a rule in the direct mapping technique. So this one, so this shows the main memory, right? So the main memory, the words are stored as blocks in the main memory, right? So each block, that is block, for example, block 0 contains 16 words, right? So each block will contain 16 words, right? So hence there is totally 4096 blocks are there in the main memory, right? So in this way it is arranged in the main memory, and first of all they are um, partitioning, or they are segmenting the main memory into 32 pages, right? So that is 32 pages means the first page will contain the block 0 from block 127, that is, and the second page will contain block 128 to block 125, to block 225, right? So that is, each page will contain 127 blocks, right? So so the first page 0 contains block 0 to block 127, that is 128 blocks. And similarly page 0, so this is this is page 0 and this is page 1. So this page 1 contains the blocks from 128 to 255. So totally there will be 128 blocks. In this way the entire memory is divided into 32 pages, and each page will contain 128 blocks of in the main memory, right? So now mapping. So now we are coming into the point, mapping. So in the mapping there is a rule that the first block of every page should be stored in the block 0 of cache memory, right? The first block of every page, that is from the page 0, the first block is block 0, and the second page the first block is block 128. Likewise in the third page the first block is block 256, right? So if we want to move the first block in any page, that in the main memory, then that first block of every page should be mapped into the block 0 of the cache memory, right? So in this way, there is block 0, block 128, block 256. So these are the three uh, um, first blocks from the three pages, and so on, right? So if in this way, the first block should be stored in the block 0, right? Similarly, the second blocks of every page, right? So for example, in the first page, the second block is block 1, and in the second page, sorry, the second block is block 129, and in the third page, the second block is block 257, right? The second page of, sorry, the second block of every page should be mapped or should be stored in the second block of cache memory, right? So that is block 1, right? I'm repeating that the second block of every page from the main memory should be mapped into block 1 of the cache memory. That is the second block 1 of the cache memory. In this way, it goes up, right? Similarly, we can say the last blocks should be stored into the that is the last blocks of every page in the main memory should be mapped or should be stored in the block 127 of cache memory, right? That is block 127, block 255, block 4095. So these blocks are the last, some of the last blocks in some pages, right? So that should be mapped into block 127, right? So this is called direct mapping, right? So in the direct mapping, uh, the main memory is divided into 32 pages, and each page will contain 127 blocks. So totally 409596 blocks will be there. And the rule here is the first block of every page should be mapped into the first block of the cache memory, and the second block of every page should be mapped into the second block of cache memory. Similarly, it goes on for the same rule is for all the blocks, and if we want to move the last block of every page from the main memory, it should be mapped into the last block, that is block 127 of the cache memory, right? So clear. And then the main memory address will have 16 bits, that is it is divided into three fields, um, that is tag field, block field, and word field, right? So the word field is 4 bits, and the block field is 7 bits, and the tag field is 5 bits, right? So now we can see how what are the purpose of this uh, block fields in the main memory address, right? So as I told, the main memory address is divided into 3 fields. The lower 4 bits of that is lower 4 bits, it selects one of the word from the block. Suppose if you are moving a block word from block 0, means block 0 contains 16 words, so it selects one word from that 16 word. So that lower 4 bits in the address represent the block in the, sorry, represent the word from the block, right? And this 7-bit determines the uh, catch position, right? So that is, it is nothing but the 7-bit is field, the next 7-bit, that is the next to the word field, the next higher 7 the next lower 7 bits determines the block field, right? So the block is nothing but the catch positions in which the block must be stored, right? So there in the we have seen in the definition or in the description, So in which position, in which cache position we should store the block from the main memory. So that is represented in the 7-bit block field, right? And next, the higher order 5-bit, it represents the tag field, right? So tag means, so here it is represented by tag. So these are the tags, right? So so the higher order 5 bits are represent the tag, right? So here it is, I have given the description for the direct mapping, that is block 0, block 128, block 256 should be loaded into block 0 of cache memory, and that is, these are the first blocks of every pages, right? So next block 1, block 129, block 2 to 257, etc. are stored at block 1 and block 1 of the cache memory. That is block 1, block 129 and 257 are the uh, second block of every page, right? So hence it is stored in the second block, block 1 of the cache memory. So this is direct mapping. And next we are going to see the associative mapping, or it is called fully associative mapping, right? So the earlier direct mapping is a simplest way, and it is not a flexible way, right? So the, and here this associative mapping is a more flexible mapping method, right? So the, in the earlier method there is a restriction that this block should be placed, this block from the main memory should be placed in this particular block in the cache memory. But in the fully associative mapping there is no restrictions, that is, any block from the main memory can be placed into any block position in the cache memory, right? So that is the fully associative mapping, right? So there is no restrictions and all. So any block, that is any block from the main memory can be blocked in, mapped into the any block position in the cache memory, right? So by that associative or the fully associative mapping is illustrated here, right? So for example, if you are considering block I, it can be mapped or it can be stored in anywhere. It can be stored in block 0, or it can be stored in block 1, or it can be stored in block 2, or it can be stored in block 3, or it can be stored in the last block, block 127, right? So there is no restriction, right? So any block from the main memory, that is, we can any store any block, that is block 0. If you want to move block 0 to the cache memory, it can be placed in any of the block 128 blocks in the cache memory. So that is the uh, fully associative mapping, right? And here in the address field there is uh, 16 bits are there, and the lower order 4-bit represent the word. That is, suppose if from the block there will be 16 words will be there, which word we are moving into the cache memory, right? So it represents the particular word from the 16 words, right? And this 12-bit represents the tag field, a tag field, right? So now you must have understood what is associative mapping, right? So next is set associative mapping, right? So set associative mapping, we can say that it is the combination of direct and fully associative mapping techniques, right? So that is, there will be, so by seeing the diagram, so there will be sets of blocks will be there in the cache memory. So here there will be the set 0, set 1, set 2, set 3 up to 6, set 63, right? So each set contains 2 blocks, right? So totally there will be 128 blocks are there in the cache memory. So each set contains 2 blocks, means the total number of sets will be 64, right? So set 0 to set 63, right? So now let us explain what is set associative mapping, right? So here in the direct mapping, I told that it is the entire main memory is divided into 32 pages. But here in set associative mapping, the entire entire main memory is divided into 64 pages, and each 64 pages will contain 64 blocks. For example, this is page 0 means it contains block 0 to block 63, that is 64 blocks will be there, right? So in direct mapping, uh, 32 pages are there and each page will contain 128 blocks. But in the case of set associative mapping, the main memory is divided into 64 pages and each page will contain 64 blocks, right? So now let us see the mapping, how the mapping is done in set associative mapping, right? So totally 64 pages are there. So here, if we want to move the first block into the cache memory position, that is the first block of every page, right? So in the, for example, first block means the block 0 is the first block of the page 0, and the block 64 is the first block of the page 1, and block 128 is the first block of the page 2, likewise. So first, if we want to move the first block from every page in the main memory, we can map it into the set 0, right? So set 0 contains two blocks, block 0 and block 1. So we can store it into any one of the block from set 0. So understood, right? So set 0, it has two blocks, block 0 and block 1. So we can map the first blocks from every pages in the main memory into any one of the blocks which is available in the set 0, right? So that is the rule in the set associative mapping. That is how the mapping is done in the set associative mapping, right? For example, if we want to move block 0 or block 63, block 64, right? So we can place it in block 0 or block 1, right? Similarly, if we want to move block 64 means if we can place it in block 0 or block 1, right? So we can place it in any one of the blocks from the set 0, right? Similarly, while moving the second blocks from every pages, right? So second block from every pages, in the sense, in the page 0 the block 1 is the second block, and in the page 1 block 65 is the second block, and in the page 3 block 129 is the second block, right? So if we want to move the second block from each page from the main memory, so it should be mapped into set 1, that is the second set, right? If we are moving the second blocks from every pages means we should map into the second set, that is the set 1 of the cache memory, right? So in the set 1 there are two blocks are there, so we can map the blocks as into any one of the blocks in the set 1, that is either in the block 2 or either in the into the block 3, right? So example, so if you are going to move block 1 into the cache memory means it can be stored it into block 2 or block 3, right? So no matter, so block 2 and block 3 belongs to the set 1, right? Similarly, block 1 block 65 means if it, also it can be stored in either block 2 or block 3. So either in either of the either block 2 or block 3, so we can store the second blocks from every pages from the main memory, so, right? So that is any one of the block from the set 1. Similarly, another one example we can give, that is the last blocks of every pages from the main memory, right? So the last blocks of every pages from the main memory can be mapped into the last set, that is set number 63 of cache memory, right? So the last block of all the 63 pages of 64 pages of main memory, if you want to move the last block from any page into the uh, cache memory means, so we can map into any one of the block which is present in the set number 63. So this is how set associative mapping works, or it functions, right? So I have explained here. So there will be for a catch with uh, for a set there will be two blocks, right? So for each set it will have two blocks, right? So here it is told that the letters in the words in bolded, that is block 0, block 64, block 128, etc. up to block 4032. These are the first blocks, right? So the first blocks from each page in the main memory is mapped into the set 0 of the cache memory, right? So and they can occupy any two block within this set, right? So two options are there. They can be mapped into any two blocks of the set 0, right? So hope you might have understood what is set associative mapping, right? So these are the what about cache memory and the three different mapping techniques in the cache memory, right? So cache memory is nothing but a portion of a static RAM which is included along with the main memory to increase the speed of the system, right? So that is to perform that is the that portion of that static RAM is called cache memory, right? So cache memory is nothing but static RAM cells. Main memory is nothing but dynamic RAM cells. So if main memory is alone there means the system will be slow. So to increase the performance or to increase the speed, we are including the cache memory, that is SRAM cells. So hence cache memory while functioning along with the main memory, the system speed will be high. It will be very high, right? And also we have seen the three different mapping techniques and how it how the three different mapping techniques works, right? So the three different mapping techniques are direct mapping, fully associative mapping, and set associative mapping. So this all about cache memory and the mapping techniques of cache memory. Thank you all.